Hello and welcome to Talking Points. I'm Dave Kelly, Director of Advanced Media Production at Cal State Long Beach. Today we're going to explore the world of modern physics. We'll examine the big questions, the issues, and the puzzles that physicists are trying to solve. My guest today is Dr. Galen Pickett. Dr. Pickett is a professor in the Department of Physics and Astronomy. Welcome, Galen, and thank you for joining us on Talking Points.
Thank you very much for having me.
Well, when we talk about physics, we're talking about both applied physics and theoretical physics. Now, we're going to spend most of our time talking about theoretical physics today, but applied physics would include things like fiber optics, lasers, telescope and camera lenses, and nuclear power. It's because of applied physics that we're able to use all of those various discoveries and convert them into technology. So now let's talk about theoretical physics and what that entails. What exactly is that, and why are people attracted to it?
Well, theoretical physics is one part of the physics enterprise that evaluates the data that experimentalists produce, but there's this feedback between ideas that theorists generate and the data that experimentalists come up with. Now, the distinction between applied and theoretical is not as sharp as you would think. I am an applied theoretical physicist, so whether applied or pure is a matter of whether your investigation of the natural world is aimed at helping people live their lives, and that's broadly applied physics, or I just want to understand what's going on here. That's pure physics. So theoretical, experimental, that's sort of the working conditions of the physicist, but the motivation is applied or pure.
So what you're telling me is that physicists tend to have maybe a foot in both worlds. They're looking for the answers to the questions that we've always wondered about, but they're also looking for ways to apply that ultimately.
Absolutely. And it is an old story in the history of physics. Someone is just trying to do something to have an advantage in the economy, to make a steam engine more efficient. That applied problem opens up entire new avenues of inquiry for pure theoretical physics work and pure experimental work. There's this feedback because it's humans doing this work. It's for all sorts of personal motivations, scientific motivations, and
all of the things that we encounter again in our daily lives, questions that we have, and then the application of those things as we move along with technology.
Indeed.
Let me ask you about your own journey. What are some of the most surprising things that you've realized about this study of physics, and what's a major revelation you have about the process and about physics in general?
So the most surprising, the thing that I could not have predicted when I was an undergraduate, and I was an undergraduate a long time ago, when I stand in front of a classroom and ask students, what were you doing in 1985? They're all, well, we weren't alive yet for another 15 years. But that's when I started the formal study of physics. And the thing that I could not have predicted then, but is an absolute bedrock of my experience now, is that anyone can learn to do this. You're talking to me today because I'm a trusted expert, I've got some expertise, I got a PhD, I've done research. But anything I tell you today about physics, anyone is about 3 years away from a part-time study, from understanding the basis of why I'm saying this. So no one has to take my word for it.
So this is not just in the realm of geniuses. I mean, it's available to anyone who has the desire to pursue the study.
Exactly. So the fact that I have a PhD in physics does not mean I'm smart. And over the next half an hour, you get a chance to make your own evaluation on that.
Okay.
What it does mean is that I had the opportunity to do this, and that I persisted in doing it. And those two ingredients, so if you want to do this kind of work, you can do it. It doesn't matter what your background is, it doesn't matter what your gender is, it doesn't matter what socioeconomic status you came from. This is your right as a human being. This is your inheritance, some of the ideas that people in my field have come up with and we'll be talking about.
Okay, well, that's all about access, opportunity, and the desire to learn, and those are all components of physics.
Yes.
Now let's talk about some issues that people are wondering about, and one of those is the Big Bang.
Yes.
And there's a television show called The Big Bang Theory that's been very popular, very successful, that kind of follows the lives of these folks that are into these very highly developed inquiries into the Big Bang Theory and so forth. So let's talk about the Big Bang Theory. Now, we all know that it was some sort of massive explosion that was essentially the creation of the universe as we know it today. But a lot of questions come up about, well, what happened before the Big Bang? If it's a series of chemicals or gaseous substances that got so compressed that they had to explode, where did those gases or chemical elements come from in the first place?
So what happened before the Big Bang, that is a matter of an intense speculation. So it is a cutting-edge research topic right now. But the fact that there was a Big Bang is one of the hallmark discoveries of astrophysics and astronomy that everyone owns. That the fact that the universe had a point where before it we don't know what happened, but everything that we know about started at one time, and things have been proceeding since.
Now that's an origination point that's also called a singularity because it can only happen one time. You can't duplicate it and make it happen again.
Well, it's singular in a mathematical physical sense in which various quantities that you can measure now in our universe. So what's the temperature in this room? Yeah, that temperature is higher the farther back you go towards the Big Bang, and higher and higher. And the fact that there's no limit on that's what's singular about it. Now, can you create those conditions in another context? Well, again, unknown. The sorts of experiments that are done at the Large Hadron Collider are reproducing on a smaller scale those events all the time. Mm-hmm. So what came before the Big Bang? The best answer to that right now that anyone will give you is, I don't know. And that's also one of the hard lessons that we had to learn as a tribe, as physicists. When you don't know, it's best to say, we don't know, yet.
But the search continues.
Indeed.
All right, well, let's move on and talk about the Earth being placed in the position of 93 miles from the sun, which is the perfect position. How did the Earth, or what became the Earth, how did it get lucky enough to be placed at 93 million miles from the sun, which is the perfect position for forming an atmosphere, for having oceans, for having resolute gravity, and all of the other things, and also the development of complex life? How did we get so lucky?
I guess because we're lucky. I mean, that's basically the answer, because if the sun had a slightly different mass, then it would have a different luminosity, and then that Goldilocks orbit would be in a different place. So the fact that there are just about half of the stars have got some sort of planetary system, half of the stars that are not binaries or trinaries, there's just lots of possibilities. And there's going to be a planet that shows up in that Goldilocks range, not all the time, but enough of the time that lucky for us, but not lucky in the context of the entire galaxy.
We won the lottery in this solar system. There might be other planets, I guess, that won the lottery in other solar systems. Is that what I'm hearing you say?
Sure. If the sun was slightly more powerful, Mars would be the place that would be the lucky spot in this solar system.
Okay, well, let's talk about the sun since we've started that conversation. What about electromagnetic energy that is generated by the sun? And we know that electromagnetic energy does a lot of things for us. One of them, obviously, is light. And we also know, as we've studied physics, that light consists of two components, if you will. One is waves, electromagnetic wave energy, and also particles. And those particles are also manifested as photons, which are very, 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 very tiny particles of light. And those photons separate out and go into different directions, but still maintain coherence or connectivity and communication. How is it that light can be both waves and particles at the same time? And why do those particles maintain some level of communication?
So the sort of particle-wave duality thing is, I think, a consequence of the fact that we just don't understand quantum mechanics the way we understand sort of person-scale, city-size phenomena. If we evolved on a savanna where we needed to catch individual electrons or find individual photons to eat, then we would understand quantum mechanics. Our senses would be built on all of those effects. So it is very puzzling how you can have something that looks like a particle, acts like a wave. It certainly acts like a wave. There's plenty of experiments to show that. It acts like a particle too. This is, one of the things that a typical undergraduate would do in a physics classroom is shoot photons like baseballs at individual electrons and catch it on the other side. Now that proves, I've done this myself. I haven't held a photon in my hand and said, oh, well, that's interesting, there's a photon. But I have thrown them like baseballs or BBs at things, had them bounce off. So the fact that they're particles, that's just a feature of the universe. Now the waviness is an emergent phenomena that comes from having a bunch of these particles all acting together. So right now you're hearing waves from my mouth. I'm causing pressure waves to be emitted from here. They're traveling, they hit your ear and they cause some mechanical vibrations, and then you interpret those sounds. The medium that's carrying that is definitely made out of particles. That's a gas. But there are so many gas particles around, the description as a continuous wave makes physical sense. And that's the sense in which electromagnetic waves are made up of photons. Now, this coherence question, two photons shot in opposite directions from an initial system, the coherence of that system and maintaining that coherence over a large enough length scale to do computations in a quantum computer or communications in quantum communications, those are technical applied physics problems that are almost solved and are going to really change almost everyone's lives. How encryption works, how communications work. Think about it. Everything that's going on in your cell phone will change because of this quantum mechanics thing. Now, the basic effect of these two photons, even though they're widely spaced apart, talking to each other, that gave Einstein an incredible amount of pause about this whole quantum project. There has to be something that is communicating between the two photons, because one of the other rock solid things, there's basically two very important things that came out of the 20th century that everyone has got a right to own. That's the theory of quantum mechanics and the theory of special relativity and general relativity. Nothing is going to win a race with a photon. Nothing can win a foot race with a photon. I think that's one way to state the principle. So if these two photons are going to be communicating with each other, they're moving at the speed of light away from each other. How could they possibly send a signal back that would catch up to something that's moving away? And again, these are slightly unsolved and unanswered questions. I'll give you what my answer is, but I'm just one physicist amongst many, and this is not my detailed area of expertise. Making measurements on these photons, even though they're spaced widely apart, the measurement is a large macroscopic device that acts sort of like you and I on sort of classical mechanics scales. So doing the measurement itself is a global thing. Even if you're talking about just this one photon, you're not doing something that's local. You've got this entire machine with all sorts of degrees of freedom, and there's plenty of room in the universe for that machine to be talking to something over on the other side of the lab where you're measuring the other photon. So I think a proper calculation of what's going on in this quantum coherence effect is going to remove the non-locality. And it is going to be just an ordinary application of the sort of physics that Richard Feynman won his Nobel Prize for.
So we're not there yet, but we're going to get there one day, is what I'm hearing you say.
I think it's a matter of clearing up some details. And so this isn't applied physics problems, but no matter, and getting those answers, there's going to be something else that's uncovered that's even more interesting than this coherence effect. And that's going to lead to new physics.
On that note, we're going to have to go to the break. And when we come back from the break, we'll talk about gravity. What is it? And also, is there actually order that forms out of chaos in the universe? Stay tuned.
Physicists ask questions. Why does the world behave as it does? They look for the interactions of matter and energy. And once they see a pattern, they develop laws and test them to see if they can predict the outcomes and get a deeper understanding of our universe. You'll find physicists in many different kinds of careers, and you can become a part of this mentally stimulating field with a degree from Cal State Long Beach.
Welcome back to Talking Points. I'm Dave Kelly, and my guest today is Dr. Galen Pickett. We're talking about modern physics and the studies that never end. And Galen, we were talking about that before the break. We were talking about light, electromagnetic energy, photons, and particle coherence. And I said we're going to talk about gravity. So we're going to start with that here in the second half. So we first learned about gravity, I guess, from Sir Isaac Newton in the 1600s when the apple fell from the tree. Mm-hmm. And that supposedly was the inspiration that got him into this theory of gravity or gravitation. So I'll give you another bite at the apple on that. So was Newton correct, or has he been surpassed by a lot of other studies and theories?
So he is correct enough to predict the motion of the solar system well enough to do navigation in the solar system. So Apollo astronauts' lives depended on Newton's predictions being quantitatively correct. So, and that hasn't changed. We still rely on Newton to navigate in the solar system. But Newton's theory has definitely been surpassed by the modern understanding of gravity that Einstein created. And Newton would have been super happy to have been a part of Einstein's work. Newton knew that there was something strange about gravity. The gravity force seems to know how hard to pull objects, not based on anything other than what the objects are made of. So that's the clue that Einstein used to make the modern theory of gravitation, the general theory of relativity. Now, both Einstein's and Newton's theories had the Big Bang implicit in them. But Newton didn't recognize that the Big Bang, some beginning of the universe, that the universe is dynamic, it can't be unchanging and everlasting. If Newton had recognized that his theory predicted a dynamic universe, he would have tore it up, never would have published it, and we would have known him for his work on optics, how light works. But this Big Bang is there in Newton's theory. It's also there in Einstein's theory, and Einstein basically rejected that idea, added some terms to his theory to make the universe be static and everlasting. The difference is there was a critical observation by Hubble that the universe is actually expanding. And then what Einstein recognized immediately, that yes, the dynamic universe is a part of my theory, it's also a part of Newton's, we're on the right track here. It's also just super fascinating that the beginning of the modern era in quantitative physical predictions starts with Newton and his gravitational work. And that is still the part that is just intractable when you put it together with quantum mechanics. The first thing that we were on solid footing with is going to be the hardest thing to put in the package at the end. And it's still unknown how to do that.
Speaking of having solid footage, what about the moon and the fact that their gravity, the gravity that exists on the moon, is about 6 times less powerful than it is here? Mm-hmm. Why is gravity so much less powerful than it is here on the Earth?
Well, the gravitational field at the surface of an object is determined by 2 things. It's how much matter there is in that object. So the moon is much smaller than the Earth, so there's less mass there. So the moon perturbs space-time a little bit less than the Earth does in its vicinity. Now, you don't get to sample all of that variation in space-time everywhere. You just get to experience it at the surface of the object. So at the surface of the object, if it's a small object, you're closer to the center of where that disturbance is. If it's a larger object, you're farther away. So there's 2 effects that balance each other. The larger the object is, the more matter it's has, so the gravity is going to be slightly larger. But you're also going to be farther away from the concentration of the mass because the object is bigger. And the combination of those 2 things basically means the gravity is stronger on the larger and more massive object. So you go to something like the moon, that's about 1/4 the size of the Earth, it works out to be 1/6 as strong. Now, if you, surface gravity on Mars is about 80% of Earth's, I think. They're comparable size planets. If you had a planet twice the size of the Earth, your your weight would be much larger. So it's just the size of the object.
So what you're telling me is that matter matters.
Exactly. It does. Period. We're done here. That's it.
We've solved it. Okay, so you were talking about dark matter and Hubble a few minutes ago, and I wanted to ask you about that. So if we're talking about the expanding universe, we also have to think about dark matter and or dark energy, I guess it really would be. The dark energy and its correlation with the expanding universe. Tell us about that. Why is the universe expanding, and how does dark energy play into that expansion?
So the expansion of the universe, before the critical observation that got everyone excited about this dark energy idea, the critical observation is that the universe is expanding. So, but the basic idea was that the expansion is basically coasting from an initial explosion. There's nothing that's driving that expansion. And it's slowing down because you've got the universe is, galaxies and stuff made out of matter. Gravity is a purely attractive force, so the farther you expand, the weaker gravity gets, and the expansion keeps going, but maybe it slows down. And that works just fine up to a certain distance looking out in the cosmos. Recent observations show that expansion is accelerating the farther away you are. It slows down a bit and then it picks up. And there is nothing in Einstein's theory of gravity that's consistent with that. Now, Einstein, the thing that Einstein added to make his universe be static and eternal, his cosmological constant, can play that role in Einstein's theory. So Einstein may have guessed the actual answer here. There may be something is providing a cosmological constant-like force, which is causing, which is overbalancing gravity and causing space itself to tear itself apart. Now, that is sort of on the edge of speculation and current research. The details of what dark energy is, and it's about 95% of the universe, is totally unknown, which gives theorists like me a big playground to come up with ideas. What's really needed here is a couple of solid observations to guide those random walks of theoretical excursions.
So dark energy is going to be a subject of great inquiry, I guess, for the foreseeable future.
It is. It is, absolutely.
Okay, well, let's talk about an area of mathematic visualization known as chaos and fractals. And we happen to have a good example of that, which is called the Mandelbrot set, which is a visualization, again, of a mathematical principle involving the fact that we have chaos, which then seems to form into some sort of order. So, as we're looking at the Mandelbrot set, you can see that this is a very well-defined series of combinations of fractals that came out of chaos that seems to suggest that order forms out of chaos. Is that true? And what does that mean if that's the case?
Well, for the Mandelbrot set itself is a delightfully intricate mathematical object, but the computer code that it would be required to generate a picture of the Mandelbrot set for yourself is about that big. So it is very easy to have a simple set of instructions that give these complicated structures. And from those 5 or 6 lines of computer code, it is impossible to predict those rich structures, those whirls and swirls and the seahorses and everything that appears in the Mandelbrot set. It's impossible to see that from those 4 lines of code. And that process, simple rules, just operating on their own, giving these complex structures, is something that is ubiquitous in physics. And everyone in Southern California, Northern California too, I'm sure, experiences this all the time. Everyone in a car, no one in a car wants to be in a traffic jam. Everyone just wants to get to where they're going. These large-scale structures that appear in traffic spontaneously just come about from cars not wanting to crash into each other. That's it. So just ordinary human behavior, simple interactions, these large-scale structures that are implicit. And that's the main problem that I'm interested in as a scientist. All of the biochemistry that makes you stay alive right now, that I'm using to speak to you, It's all very simple molecular structures. When you get down to it, it's just nuclei and electrons doing what they do. And yet, you put all that stuff in a vat, you wait a couple billion years, and these interesting structures appear following the simple pieces to the complicated structures, that process of emerging phenomena. That is one of the big unanswered questions in physics. And it's one of the big unanswered questions that human beings have been asking as long as we've had questions. So what is life? What makes you be a living system but your notepad is not? I mean, if I'm looking as a cold-hearted physicist, there's a collection of atoms, there's a collection of atoms.
Same
I don't see any
elements,
difference.
why are they different? Yeah.
Exactly. There's something functional in the organization and the self-organization that is going to be the key to many of the things that are just super interesting about the universe.
Something forms that spirit of animation, if you will, that takes it from a static object to a lively, alive kind of object. Okay, we're running out of time, Galen, but I wanted to talk about that since you brought it up about elements and not all of them coming together to form a lively activity. We have just a minute. Star Trek. Beam me up, Scotty. Teleportation, where people go into the chamber and they become dissolved and then they're moved over and teleported to another location and then reanimated and brought back together in less than a minute. Obviously, we can't do that today. Is that theoretically possible or not?
Well, if your mind has got any sort of quantum thing to it, so if quantum mechanics is essential for consciousness, then no. There's going to be uncertainty principles, hard constraints that are going to make it impossible to take a quantum system and measure it without destroying it. So making multiple copies of it is just going to be impossible. Now, if the important structures that are making you and me experience me as individual human beings are just the connections of individual neurons, I can imagine mapping those and maybe not making another person out of it, atom by atom, but maybe taking those connections and putting them in a computer, making a copy of my consciousness. So yes and no. I can imagine sending an agent of mine somewhere in 100 years, over a modem, have them do something, come back and report to me. I think that will happen.
Okay, it's a little bit like the printers that we have, the 3D printers that we have today in a way.
Exactly.
Okay, very good. On that note, we're going to have to close the program, but I really appreciate you coming in today and sharing with us these very complex theories.
Thank you very much.
And thank you for joining us on this edition of Talking Points. Please be sure to join us again soon for the next episode. Until then, I'm Dave Kelly. Have a nice day.